Hey guys, welcome to this news story. Today, we turn our eyes to the moon, the silent companion that has guided Earth for billions of years. It lights our nights, pulls our oceans, and even shapes the way life has grown here. But imagine just for a moment that it disappeared, gone in an instant. The tides would shift, the night sky would feel empty, and the balance that holds our planet steady would start to wobble. The moon has always been there, slowly moving through the sky, keeping time with Earth's rotation. Without it, storms, oceans, and even the path of our planet itself could change in ways we barely understand. In this video, we explore what would really happen if the moon vanished and why its presence has been so crucial for life on Earth. The moon is Earth's only natural satellite, a body of rock and dust that orbits the planet at an average distance of roughly 384,400 kilometers. Its mass is approximately 1/80th that of Earth, yet its gravitational pull is sufficient to produce noticeable effects on the surface and interior of the planet. The moon completes one orbit around Earth every 27.3 days relative to the stars and 29.5 days relative to the sun, creating the familiar cycle of lunar phases. These motions are the result of precise gravitational interactions between Earth and the moon, coupled with the rotation of the planet itself. The moon does not generate light of its own, but reflects sunlight, which gives it a bright presence in the night sky and provides a slow, predictable change in illumination over the lunar month. Its formation is most widely explained by the giant impact hypothesis. Early in the solar system, a body roughly the size of Mars collided with the young Earth, ejecting large amounts of material into orbit. This material coalesced under its own gravity to form the moon. The resulting satellite has a composition similar to Earth's mantle, which has been confirmed through rock samples returned by Apollo missions. The moon's gravitational influence is responsible for a significant part of Earth's dynamic stability. Without it, the rotation of the planet would be less regular, and its axial tilt could vary more wildly over time, altering the distribution of sunlight and affecting global climates. These effects occur gradually, over thousands to millions of years, but they are fundamental to the way Earth functions. The moon exerts a force on Earth known as tidal gravity. This force pulls on both the oceans and the solid body of the planet. In the oceans, this pull generates tides, creating a continuous cycle of rising and falling water levels. High tides appear on the side of Earth, facing the moon, as well as on the opposite side, due to the centrifugal effect created by the Earth-Moon system's rotation around a common center of mass. Tides are amplified when the sun aligns with the moon during full and new phases, producing what are known as spring tides. During the first and third quarters of the lunar cycle, the sun and moon are at right angles relative to Earth, producing any tides when the range of ocean movement is minimized. These regular, predictable tides are crucial to marine ecosystems, nutrient mixing, and the movement of water along coastlines. Without the moon, tidal ranges would be far smaller, driven only by the sun, and ocean behavior would change in ways that could disrupt ecological balance. The gravitational interaction between Earth and the moon also has an impact on the rotation of the planet. Tidal friction causes a transfer of angular momentum from Earth to the moon, gradually slowing the planet's rotation. This effect has increased the length of an Earth day from approximately 22 hours in the distant past to the 24-hour period observed today. Simultaneously, the moon is moving away from Earth at a rate of roughly 3.8 centimeters per year. Over billions of years, this gradual shift has contributed to the stability of Earth's climate by preventing extreme changes in rotation and tilt. Were the moon to vanish suddenly, this dynamic balance would be interrupted, and Earth's rotation could experience sudden adjustments, although the full effects would take years to manifest in measurable ways. The moon also contributes to the stability of Earth's axial tilt. The planet's axis is inclined at about 23.5 degrees relative to its orbit around the Sun. This tilt is responsible for the seasonal changes experienced around the globe. The presence of the moon dampens variations in tilt caused by gravitational interactions with other bodies in the solar system, particularly the Sun and Jupiter. Without this stabilizing influence, Earth's axial tilt could oscillate more widely over thousands of years, potentially leading to more extreme seasonal variations and shifts in climate patterns. These changes would affect temperature distribution, precipitation patterns, and the long term behavior of polar ice sheets. The moon's steadying effect ensures a relatively predictable climate over geological timescales, which has allowed ecosystems to evolve and adapt within relatively stable conditions. The visible phases of the moon are the result of its orbit around Earth and the relative positions of the moon, Earth, and Sun. When the moon is between Earth and the Sun, the side facing Earth is dark, producing a new moon. When the moon is on the opposite side of Earth from the Sun, its near side is fully illuminated, producing a full moon. Between these extremes, the moon appears partially lit in shapes known as crescents and quarters. These phases govern not only the visual cycle, but also the timing of tides and certain biological processes in animals. Many marine organisms, including corals and fish, synchronize spawning and migration with the lunar cycle. The disappearance of the moon would remove this natural timing mechanism, potentially disrupting cycles that are deeply embedded in ecological systems. The moon has a synchronous rotation with Earth, meaning the same hemisphere always faces the planet. This is the result of tidal locking, a process in which the gravitational pull between two bodies gradually synchronizes rotation with orbital motion. The far side of the moon, often called the dark side, remained unseen until the era of space exploration. The uneven distribution of mass within the moon, including large basins and mountains, contributes to subtle variations in its gravitational pull on Earth. These variations affect ocean currents, the movement of Earth's crust, and even the flow of molten material within the mantle. The absence of the moon would eliminate these gravitational interactions, which could have minor but measurable effects on geological processes and the behavior of fluids on the planet. Lunar eclipses occur when Earth passes between the Sun and the Moon, casting a shadow across the lunar surface. Solar eclipses happen when the Moon passes between Earth and the Sun, temporarily blocking sunlight. Both phenomena are direct results of the precise distances and sizes of the Sun, Moon, and Earth. The alignment that produces eclipses is a small but measurable demonstration of the Moon's influence on Earth. These events have historically provided opportunities for scientific observation, including the study of the Sun's corona, the measurement of the Moon's distance, and confirmation of general relativity. In a scenario where the Moon disappears, these predictable alignments would vanish, removing both the practical and observational aspects of these interactions. Beyond gravitational and orbital effects, the Moon affects the solid body of Earth. Its pull slightly stretches and compresses the planet, producing what is known as Earth tides. These movements are subtle compared to ocean tides, but are measurable with sensitive instruments. Earth tides can influence volcanic activity, the movement of fault lines, and the propagation of seismic waves. The Moon's influence on these processes is continuous and regular, providing a slow, rhythmic modulation to the planet's geophysical activity. The sudden removal of the Moon would alter the balance of stresses within the crust, potentially changing patterns of seismic and volcanic activity over time, though the effects would manifest gradually. The Moon also moderates the orientation of the equinoxes. The gravitational relationship between Earth and the Moon ensures that the points where the Sun crosses the celestial equator shift very slowly over time. Without the Moon, precession would occur more rapidly, causing the timing of equinoxes to change over centuries. This would influence the patterns of solar radiation reaching different latitudes, altering the timing and intensity of seasons. Agricultural cycles and natural rhythms, long adjusted to predictable solar paths, would gradually be disrupted. The moon's presence thus provides a stabilizing rhythm for both environmental processes and the long term behavior of Earth's orbit. The moon contributes to the overall energy balance of Earth. Its gravitational pull affects ocean mixing, which helps distribute heat around the planet. By moderating the movement of water and influencing the circulation of air masses indirectly, the moon plays a subtle role in climate regulation. Its absence would alter these patterns, reducing some of the mixing efficiency in oceans and potentially changing weather systems over long timescales. The effects would be distributed unevenly, affecting equatorial currents differently from polar regions, and influencing precipitation, temperature gradients, and wind systems across the globe. The moon's gravitational presence, though often taken for granted, is a continuous force shaping the dynamic balance of the planet in both obvious and subtle ways. Tides are the regular rise and fall of ocean waters along coastlines, produced primarily by the gravitational pull of the moon. As Earth rotates, the water closest to the moon experiences a stronger attraction, forming a bulge on the side facing the moon. On the opposite side of Earth, another bulge appears due to the centrifugal effect created by the Earth Moon system, rotating around a shared center of mass. These bulges move slowly around the globe as Earth spins, producing cycles of high and low water levels at different locations. The timing of these cycles depends on the relative positions of the Moon, Earth, and Sun, creating a pattern that repeats approximately every 12 hours in most locations. While the Sun also exerts a gravitational force on Earth's oceans, it is about half as strong as the Moon's influence. When the Sun and Moon align, the tidal effects combine, producing higher than normal spring tides. When they are at right angles, the tidal effects partially cancel each other, producing lower nap tides. The amplitude of tides varies across the planet. Coastal shape, but water depth, and local geography all influence the height and timing of the tidal bulges. Narrow bays or estuaries can amplify the rise of water, while shallow continental shelves slow its movement. The rhythmic motion of tides drives currents along coastlines, redistributing nutrients and sediments. These currents carry plankton, the smallest forms of life in the ocean, as well as oxygen and minerals. In this way, tides are a critical factor in maintaining the health of marine ecosystems. Mangroves, salt marshes, and coral reefs rely on the regular movement of water to bring food and remove waste. Without the moon's pull, tides would shrink considerably, leaving many coastal areas with reduced water exchange and potentially altering the distribution of life along the shoreline. Tidal forces also affect the open ocean, not just shallow coastal regions. The slow rise and fall of ocean waters produces horizontal movement known as tidal currents. In deep water, these currents are subtle but measurable, interacting with larger oceanic flows to influence global circulation patterns. The movement of water helps to transfer heat from equatorial regions toward the poles, stabilizing temperatures over long distances. Tidal mixing prevents layers of water from becoming completely static, bringing oxygen to deeper areas and distributing nutrients throughout the water column. Without the moon, this mixing would be weaker, reducing the efficiency of global ocean circulation and changing the distribution of temperature and salinity over time. These changes would ripple through climate systems, subtly altering wind patterns, storm intensity, and precipitation patterns over decades or centuries. High tides affect erosion and sediment transport along coastlines. As water levels rise and fall, waves reach higher on beaches and shorelines, moving sand, silt, and debris. Estuaries experience periodic flooding and drainage, carrying organic material into rivers and coastal wetlands. The cyclical nature of tides also forms natural barriers that protect inland areas from saltwater intrusion. With diminished tides, these processes would slow, potentially allowing sediments to accumulate unevenly or letting seawater penetrate further into coastal soils. The regular clearing of debris and replenishment of materials in tidal zones is an essential part of coastal maintenance. Changes in tidal force would modify these processes, altering the shape and composition of shorelines gradually over time. Tides influence temperature and salinity in coastal waters. When ocean water rises and falls, it brings cooler water from deeper areas to the surface and carries warmer surface water toward the land. This exchange helps regulate local climates, supporting marine life that depends on specific ranges of temperature and salt concentration. For example, certain shellfish require a particular salinity to develop shells, while some algae need the mixing of nutrients from deeper water to bloom effectively. The moon's absence would reduce this vertical and horizontal exchange, potentially impacting species dependent on these precise conditions. Over time, shifts in local ecosystems could cascade into larger patterns, affecting fisheries, food webs, and coastal vegetation. Tidal cycles also have an influence on ocean currents in polar regions. In areas covered by ice, tidal forces push water beneath the ice sheets, facilitating the movement of nutrients and gases. The slow rise and fall of tides under ice shelves can prevent stagnation of cold water and allow for heat and salt exchange between different water layers. These movements contribute to the formation of dense cold water that sinks and drives the thermohaline circulation, often referred to as the global conveyor belt. Without the moon, the formation of these dense water masses would be slower, weakening a major driver of long distance ocean currents and subtly affecting the distribution of temperature and salinity across the globe. The gravitational pull of the moon creates predictable tidal peaks that have been used for centuries to navigate waterways. Ships rely on knowledge of high and low tides to enter ports safely, and tidal calendars guide the timing of fishing activities. Tidal energy, a renewable resource, depends on the moon's pull to generate consistent flows of water that can turn turbines. A sudden disappearance of the moon would reduce tidal ranges and currents, limiting the potential for tidal energy and complicating human management of coastal and marine resources. The daily rhythm of tides is one of the most tangible ways in which the moon exerts influence over both natural systems and human activity. In addition to the gravitational effect, tides are influenced by the shape and rotation of the Earth itself. The equatorial bulge of Earth, caused by its rotation, interacts with the tidal pull to create slight asymmetries in tidal height around the globe. These asymmetries lead to phenomena such as amphidromic points, where tides rotate around a central node with minimal vertical change. Such points show the complexity of tidal movement, as water does not rise and fall uniformly, but circulates in patterns dictated by gravity, rotation, and ocean basin geometry. Without the moon, these complex patterns would simplify dramatically, leaving a weaker and more uniform tidal response, driven only by the sun. Tides also affect the exchange of gases between the ocean and atmosphere. Rising and falling waters facilitate the release of oxygen from the surface to the air and the absorption of carbon dioxide from the atmosphere into the ocean. These exchanges are essential to maintaining chemical balance in both environments. The movement of water, driven by lunar tides, accelerates mixing and contributes to the overall health of ocean ecosystems. Reducing tidal strength would slow these processes, changing the rate at which gases are cycled and potentially influencing the long-term carbon balance of the planet. Some regions experience extreme tidal ranges due to local geography. The Bay of Fundy, for example, can see differences in water height of up to 16 meters between low and high tide. These high tides result from the alignment of lunar forces with the shape of the bay, which funnels water into a narrow space. Such extreme tidal regions highlight how lunar gravity interacts with Earth's features to create strong, localized effects. If the moon disappeared, these extreme tides would disappear entirely, and the specific ecosystems and human infrastructure that rely on them would undergo gradual adjustment to the new, smaller tidal range. Tidal resonance occurs when the natural period of water movement in a bay or estuary matches the frequency of the tides. This resonance amplifies water motion, creating higher peaks and stronger currents. Many coastal regions experience enhanced currents due to this effect. The moon's disappearance would remove the driving force behind tidal resonance, reducing water movement in these areas and altering the dynamics of sediment transport, nutrient cycling, and biological activity in estuaries. Over long periods, this would shift the physical and ecological characteristics of coastal zones, modifying habitats for many species. Tides are closely linked to the moon's orbit, which slowly changes over time. The distance between Earth and the moon increases gradually, causing a small but measurable change in tidal amplitude. Over millions of years, tides have grown weaker as the moon moved further away. This long term trend shows the sensitivity of Earth's oceanic system to lunar gravity. If the moon were removed entirely, tidal cycles would no longer exist in their present form, replaced by the weaker, less regular influence of the sun alone. The consequences would be global, affecting ocean currents and climate patterns and the biological systems that depend on the rhythmic rise and fall of waters. The moon's gravitational pull is not merely a nighttime spectacle in the sky, it is a constant force shaping the physical and biological state of Earth's oceans. Earth rotates on its axis once approximately every 24 hours, a motion that defines the cycle of day and night. This rotation is gradually affected by tidal forces, which arise primarily from the moon's gravitational pull. As ocean water is drawn toward the moon, the movement of water produces friction against the ocean floor and the planet's crust. This tidal friction transfers energy from Earth's rotation to the moon's orbit. Over long periods, this transfer of angular momentum causes Earth to slow down gradually, increasing the length of a day. In the distant past, days were much shorter. Fossil records and growth patterns in ancient corals indicate that around 4 billion years ago, a day may have lasted only about 22 hours. This process has been consistent, allowing scientists to measure the historical evolution of Earth's rotation by examining geological and paleontological evidence. The rate at which Earth's rotation slows is small but measurable. Modern observations show that the length of a day increases by approximately 1 millisecond every 70 to 80 years. Though this change seems minimal on a human timescale, it accumulates significantly over millions of years. The gradual deceleration has implications for the timing of astronomical observations, the calculation of calendars, and the synchronization of clocks fits with natural day-night cycles. The moon's presence ensures that this slowing is steady and predictable. Without the moon, the mechanism of tidal friction would be greatly diminished, as the sun's tidal influence is roughly half as strong. Consequently, Earth's rotation would no longer decelerate at the same rate, potentially causing abrupt or uneven shifts in rotational speed over long periods. The transfer of angular momentum from Earth to the moon also causes the moon to move away from Earth slowly, at a rate of roughly 3.8 centimeters per year. This gradual separation has a feedback effect on the rotation of the planet, further stabilizing the system. As the moon retreats, its gravitational pull weakens slightly, reducing the amplitude of tides. This subtle reduction in tidal force slows the rate of angular momentum transfer, creating a balance between the slowing of Earth and the outward movement of the moon. The entire system has evolved over billions of years to reach its current state, where the moon's orbit and Earth's rotation are closely interconnected. A sudden disappearance of the moon would instantly remove this mechanism, leaving Earth without the stabilizing transfer of energy that has shaped its rotation for millennia. If the moon vanished suddenly, the immediate loss of tidal friction would stop the transfer of angular momentum. Although the change in day length would not be noticeable within a single day, over decades and centuries, the long term effects would become apparent. The Earth might continue to slow down under the influence of the Sun's weaker tidal pull, but this process would be irregular and uneven. The balance that has maintained a relatively consistent 24-hour cycle would be disrupted. Some regions could experience slight variations in day length, while global synchronization of timekeeping systems would be affected. The planet's rotation, previously moderated by the moon, would adjust over time to the new distribution of forces acting upon it. Tidal friction not only affects rotation, but also contributes to internal energy. Dissipation within Earth. The movement of water and the associated stress on the planet's crust generates heat in the mantle and crust. While the amount of energy is small compared to geothermal heat, it represents a continuous input that slightly modifies convection currents in the mantle. Mantle convection, in turn, drives plate tectonics and influences volcanic activity. The removal of the moon would alter this contribution, reducing the regular input of tidal energy and subtly changing the forces acting on the interior of the planet. These changes would occur gradually, but would affect the long term evolution of Earth's geophysical processes. Earth's rotation is also linked to the stability of the planet's axis. The momentum of a rotating body interacts with gravitational forces to resist changes in tilt. With tidal friction from the moon acting consistently, the planet's rotation has been smoothed and stabilized over time. Without the moon, rotational momentum would continue, but the stabilizing effect would diminish. Over thousands to millions of years, variations in tilt could become more pronounced, altering the distribution of solar radiation across the surface and influencing climate patterns. Although this is a long term effect, it illustrates the moon's role in maintaining not only day length, but also overall planetary stability. The interaction between rotation and tides has a cascading effect on atmospheric circulation. The rotation of the planet contributes to the Coriolis effect, which shapes wind patterns and storm trajectories. Changes in day length would modify the speed at which air moves across the surface, slightly altering prevailing winds and the movement of weather systems. Although immediate effects would be subtle, over centuries, the cumulative impact could influence climate zones and seasonal behavior. The moon's gravitational pull ensures that the rotation and tidal cycles maintain a consistent relationship, providing a predictable pattern for atmospheric dynamics. Historical records, such as observations of eclipses and ancient astronomical texts, provide evidence for the gradual slowing of Earth's rotation. Comparisons of ancient eclipse timings with modern calculations show that the length of a day has increased steadily over the last 2 millennia. Lunar influence has been the dominant factor in this evolution, with tidal friction producing small but cumulative effects. Without the moon, this historical trajectory would end abruptly, leaving only solar tides to affect the planet's rotation. The rate of change would be slower and more irregular, removing the consistency that has guided timekeeping, seasonal calculations, and human activities dependent on predictable day lengths. The relationship between rotation and tidal forces also affects oceanic behavior. As Earth rotates, the movement of water in response to tides interacts with currents and the distribution of heat. The slowing of rotation slightly modifies the timing of tides relative to the surface, which can influence the patterns of tidal currents along coasts and in the open ocean. These currents distribute heat and nutrients, connecting rotation, tidal forces, and the movement of energy across the planet. Without the moon, this interconnected system would be disrupted, reducing the efficiency of heat and material transfer in oceans and changing the timing of coastal water movements. In addition to day length, the moon's influence on rotation affects the synchronization of biological rhythms. Many organisms rely on the steady cycle of day and night, as well as tidal cycles, to regulate feeding, reproduction, and migration. The gradual slowing of Earth's rotation ensures that these cycles progress predictably over long periods. Without lunar induced stabilization, the timing of days could drift more quickly over geological time, altering the environmental cues that many species depend on. This effect is not immediate, but contributes to the larger pattern of life's adaptation to the planet's rotational behavior. The combination of tidal friction and angular momentum transfer has shaped the evolution of Earth's rotation into its present form. The 24-hour day is the product of billions of years of interaction between Earth and the Moon. Without the Moon, the rotation would no longer follow this precise, stable rhythm. The planet would continue to turn, but small irregularities would accumulate over centuries, slowly changing the length of days and the structure of timekeeping. The moon's presence has been integral to the balance that allows Earth's rotation, day length, and associated physical processes to maintain stability over geological and biological timescales. Earth's axis is tilted at an angle of approximately 23.5 degrees relative to the plane of its orbit around the Sun. This tilt is responsible for the seasonal changes experienced across the planet as different latitudes receive varying amounts of sunlight throughout the year. The Moon plays a critical role in stabilizing this tilt. Its gravitational pull exerts a torque on Earth, which counteracts perturbations caused by the Sun and other planets. Without the Moon, the axis would be subject to larger variations in orientation, which would gradually increase over thousands to millions of years. Those shifts, though slow, would alter the angle at which sunlight reaches the surface, changing the intensity and distribution of seasons across the globe. The stability provided by the moon ensures that seasonal changes remain relatively consistent over long periods. The tilt does not fluctuate dramatically, allowing ecosystems to adapt to predictable patterns of temperature, precipitation, and sunlight. Plants and animals synchronize their growth, reproduction, and migration with these cycles. Without the moon's stabilizing effect, the tilt could oscillate more widely, potentially varying by tens of degrees over geological time. Such fluctuations would amplify seasonal extremes, causing summers to become hotter and winters colder at certain latitudes. At other times, the tilt could decrease, reducing seasonal variation and leading to milder climates in regions accustomed to significant seasonal shifts. The moon's presence therefore maintains a slow but reliable rhythm to the planet's climate. Polar regions are particularly sensitive to changes in axial tilt. The orientation of the poles relative to the sun determines the length of day and night during different seasons. With a stable tilt, polar summers experience continuous daylight, while polar winters have long nights. These light cycles influence ice formation and melting, which in turn affects sea levels and global ocean currents. Without the moon, shifts in tilt could alter the timing and duration of polar sunlight. Ice sheets might grow or shrink in ways that deviate from current patterns, causing changes in the volume of water in the oceans. Even small adjustments in polar ice coverage can influence the reflection of sunlight, known as albedo, further affecting temperatures across the planet. Changes in axial tilt would also impact the distribution of solar energy across mid-latitude and tropical regions. In areas near the equator, variations in tilt could modify the angle at which sunlight strikes the surface, influencing the intensity of heat received. Over thousands of years, this would gradually change temperature patterns, potentially affecting wind systems and precipitation cycles. Areas currently reliant on monsoon systems or predictable rainfall patterns could experience shifts in timing, strength, or location of seasonal rains. These changes would influence vegetation patterns, soil moisture, and the overall energy balance of ecosystems. The moon's stabilizing effect on tilt maintains consistency in these processes over geological timescales. Ocean circulation is indirectly influenced by axial tilt. Variations in tilt affect the distribution of solar heating, which drives temperature differences between regions. These differences create density gradients in water that help establish currents, including large scale patterns such as the thermohaline circulation. If Earth's tilt were to oscillate widely in the absence of the moon, changes in solar heating could alter the strength and direction of ocean currents. This would impact the movement of heat around the planet, potentially changing climate patterns over decades or centuries. The moon's gravitational presence therefore contributes not only to seasonal stability, but also to the regulation of long term ocean and climate systems. Atmospheric patterns are closely tied to axial tilt. The position and strength of the jet streams, as well as prevailing winds, depend on temperature gradients created by sunlight. Shifts in tilt would modify these gradients, causing changes in wind behavior and storm tracks. Over long periods, regions might experience alterations in the frequency and intensity of storms, as well as the distribution of precipitation. The regular tilt maintained by the moon allows atmospheric circulation to remain within predictable ranges, stabilizing weather systems across continents. Without the moon, long term climate models would become less predictable, as variations in tilt would introduce an additional source of change in global circulation. The effect of tilt on day length and seasonality also influences soil formation and erosion. In regions with strong seasonal variation, alternating periods of warmth, cold, wet, and dry conditions contribute to the breakdown of rock and redistribution of sediments. Large oscillations in tilt could accelerate or slow these processes depending on how sunlight exposure changes over time. Over millennia, landscapes could evolve differently, with variations in the development of river systems, soil composition, and the distribution of sediments along coasts and floodplains. The moon's role in stabilizing tilt helps maintain a gradual, consistent pace for these surface processes. Temperature gradients caused by axial tilt affect the growth of vegetation, which in turn influences carbon cycling in ecosystems. Stronger seasonal swings could alter the timing of photosynthesis and respiration in plants, affecting the balance of carbon absorbed and released. These changes would ripple through food chains, influencing herbivores and predators, as well as decomposer organisms. Without the moon, greater fluctuations in tilt could produce a less predictable cycle of energy and nutrient flow in terrestrial ecosystems, gradually altering climate feedbacks over long periods. Ice ages and glacial cycles are also linked to variations in tilt, along with other orbital parameters. Even small changes in axial tilt can influence the advance and retreat of glaciers. With the moon maintaining a relatively constant tilt, ice ages occur over predictable intervals influenced primarily by orbital variations. Without the moon, larger and less predictable oscillations in tilt could disrupt these cycles, potentially leading to irregular glacial advances and retreats. The timing, intensity, and location of glacial periods would shift, affecting global sea levels, ocean currents, and habitats for both terrestrial and marine species. Lunar stabilization affects equatorial regions as well. In the tropics, where solar radiation is relatively constant, a stable tilt ensures that the position of the sun at noon changes gradually over the year. Without this consistency, areas near the equator could experience greater variation in solar angles, affecting local climates. Rainfall patterns driven by convection would shift in timing or intensity, influencing river flows, groundwater recharge, and agricultural potential. The moon's gravitational influence ensures that equatorial climates remain relatively consistent despite other changes in the Earth-Sun system. Seasonal cycles influence biological rhythms. Many organisms time reproduction, migration, and growth according to predictable seasonal cues, which depend on the stable tilt of the planet. Changes in axial orientation would modify the length and intensity of seasons, affecting the availability of food, water, and habitat conditions. The moon indirectly supports these cycles by keeping axial tilt within narrow limits, allowing ecosystems to function on a predictable rhythm. Without the moon, Gradual shifts in seasonal intensity could force adaptation in species over thousands of years, altering ecological dynamics. The interaction between tilt, insolation, and global climate extends to precipitation and humidity patterns. Temperature differences between land and ocean drive evaporation and cloud formation. With a stable tilt, these patterns remain within certain bounds, maintaining climate zones. Variations in tilt without the moon could move climate zones north or south, changing where deserts, rainforests, and temperate regions develop. These shifts would occur slowly but persistently, reshaping the distribution of habitats over millennia. The moon's presence ensures that these changes remain gradual and predictable. The long term stability of Earth's climate is a product of the moon's influence on tilt, rotation, and tidal forces. By moderating axial orientation, the moon reduces the amplitude of seasonal extremes and preserves consistent polar and equatorial conditions. Its removal would set in motion slow but significant alterations in climate, ocean circulation, and atmospheric behavior. The rhythms of sunlight, temperature, and seasonal change, so familiar to life on Earth, are tied closely to the presence of the moon. Without it, the planet would continue to orbit the sun, but the patterns governing climate and the timing of seasons would become less certain, and long term environmental balance would gradually shift. The moon is the primary source of natural light at night on Earth. Its brightness is not constant, but changes in a predictable cycle known as the lunar phases. During a full moon, the side of the moon facing Earth is fully illuminated by sunlight, producing the brightest nights. At new moon, the near side is dark, the night is relatively dim. Between these extremes, the moon displays crescent and quarter shapes as portions of its surface are lit. The cycle from new moon to full moon and back takes approximately 29 and a half days, creating a monthly rhythm of changing night brightness. This cycle governs patterns in illumination that many animals and ecological processes have adapted to over millions of years. Moonlight intensity is influenced by the angle of sunlight reflecting off the lunar surface and the distance between Earth and the moon. The moon's surface is covered with regolith, a layer of fine rock and dust, which reflects only about 12% of sunlight. Despite this low reflectivity, the light reaching Earth is sufficient to illuminate landscapes at night, casting shadows, highlighting contours, and creating areas of contrast. During full moons, nocturnal visibility can be dramatically increased, aiding navigation for some species while exposing others to predators. The moon's motion across the sky produces slow changes in the location and angle of light, creating a predictable pattern that moves gradually with Earth's rotation. Nocturnal organisms rely heavily on these patterns of lunar illumination. Animals such as certain species of owls, bats, and insects time their activity based on the availability of moonlight. Predators may hunt more effectively under bright nights, while prey species may reduce activity to avoid detection. The moon's phases create a regular schedule of light intensity, influencing the behavior of entire populations. For example, sea turtles time hatching to coincide with darker nights near the new moon to reduce exposure to predators, while crabs and other shore-dwelling animals adjust foraging activity according to the brightness of the moonlit tide. The removal of the moon would eliminate these regular cues, forcing many species to rely solely on other environmental signals or develop new behavioral adaptations. The moon's illumination also interacts with plant biology. Many photosensitive processes in plants are tuned to cycles of light and darkness. Some seeds rely on lunar cycles to regulate germination timing, while flowering and growth patterns in certain species are subtly influenced by the nighttime light environment. Artificial light has a small but measurable impact on these processes, demonstrating the sensitivity of plants to nocturnal illumination. Without the moon, the intensity and duration of nightlight would be greatly reduced, altering the environmental cues that guide biological rhythms in both plants and animals. Over time, ecosystems would gradually adjust to darker nights, potentially affecting the timing of reproduction, feeding, and growth cycles. Tides, also governed by the moon, influence nocturnal activity. Rising tides during certain lunar phases affect the accessibility of food sources and habitat areas for nocturnal species. Crabs, mollusks, and fish adjust feeding and movement according to tidal height, which correlates with the position of the moon. Birds and mammals that feed along shorelines or in wetlands may synchronize movement and foraging with tidal conditions. The disappearance of the moon would reduce tidal amplitudes, altering the timing and availability of resources. This change would ripple through food webs, affecting the success and behavior of predators and prey that rely on predictable tidal cycles coupled with lunar illumination. Moonlight also shapes the migration patterns of some species. Nocturnal. Migratory birds and insects use the moon for orientation, tracking its position to maintain navigational bearings over long distances. The cycle of lunar phases provides a schedule for timing departures and arrivals, with darker nights sometimes preferred to reduce predation risk. Insects, such as moths, navigate using the moon and stars as reference points, balancing orientation against exposure. Removal of the moon would eliminate these cues, forcing species to rely more heavily on other celestial or environmental signals, which could introduce increased navigational error and energy expenditure over long migrations. Many marine organisms synchronize reproductive cycles with the lunar cycle. Coral spawning, for instance, often occurs shortly after full moons, timed to coincide with peak tidal conditions that increase the dispersal of gametes. Other fish and invertebrates use the moon as a signal for breeding or aggregation. Moonlight helps regulate these behaviors by providing a consistent environmental cue that repeats monthly. Without the moon, these reproductive cycles would lose their primary timing mechanism, potentially reducing synchronization and affecting the success of species that depend on coordinated mass spawning events for reproduction. The moon also affects nocturnal predator prey dynamics. During full moons, increased illumination improves the hunting efficiency of nocturnal predators, such as owls and big cats, in open environments. Prey species often modify behavior to reduce exposure, seeking shelter, or shifting activity to dimmer periods. This dynamic contributes to population balance, as predation pressure and prey availability remain coupled with predictable lunar cycles. If the moon disappeared, these light driven patterns would vanish, leading to more constant nocturnal darkness and changing predator prey interactions. Some species might expand activity into formerly illuminated periods, while others would adapt to remain hidden, gradually reshaping nocturnal behavior across ecosystems. Lunar illumination also impacts human activity. Before artificial lighting, humans relied on moonlight for nighttime navigation, agriculture, and social gatherings. The predictability of the lunar cycle influenced calendars, work schedules, and cultural events. While modern technology has reduced dependency on natural nightlight, historical observation shows that humans have long integrated lunar brightness into daily life. Removal of the moon would eliminate this natural pattern, creating consistently darker nights and removing a long standing environmental rhythm. The interaction of moonlight with nocturnal ecosystems extends to microhabitats. Forest undergrowth, open grasslands, and desert environments all experience variations in night illumination depending on the phase of the moon. Small mammals, amphibians, and insects adjust movement and feeding to correspond with light intensity. This predictable variation reduces the risk of predation while allowing continued access to food sources. Without the moon, these microhabitats would experience uniform darkness, altering the spatial distribution and behavior of nocturnal species and influencing competition for resources. Moonlight also contributes indirectly to environmental temperature regulation. Bright nights can slightly increase radiative heating of surfaces compared to darker nights, affecting the thermal microenvironment for small animals and insects. The slow rotation of light across the landscape creates temporal variation, allowing species to time activity in warmer or cooler conditions. The absence of the moon would reduce these fluctuations, producing consistently darker nights with subtly different temperature dynamics, which could influence energy budgets and survival strategies of small nocturnal organisms. Well, nocturnal light cycles controlled by the moon support seasonal behaviors. Certain species rely on the combination of moon phase and seasonal timing to determine when to mate, migrate, or forage. For example, some insects emerge during specific lunar phases in spring and summer to take advantage of optimal conditions. Birds and mammals may synchronize breeding or movement with these predictable cycles. The moon's disappearance would eliminate these monthly signals, forcing organisms to rely solely on other environmental cues, such as temperature or day length, which may not provide the same precision, gradually altering long term ecological timing. Artificial light has demonstrated the sensitivity of organisms to nocturnal illumination. Light pollution can mimic or interfere with the patterns established by the moon, affecting feeding, migration, and reproduction. Observations of these effects illustrate the importance of natural lunar cycles in shaping ecological behavior. Without the moon, natural light cycles would be replaced by near complete darkness, with artificial lighting only providing inconsistent or localized cues. The rhythm of nightlife for countless species would change, with adjustments occurring slowly as ecosystems adapt to the absence of lunar guidance. The moon's role in nighttime illumination links to broader ecological processes. Moonlight, tidal movement, and nocturnal activity are interconnected, producing rhythms that influence energy flow, nutrient cycling, and population dynamics. The disappearance of the moon would remove the primary source of these cycles, replacing them with dimmer, less predictable nights. Ecological processes that have evolved in concert with the lunar cycle would be disrupted, forcing gradual adaptation in organisms across terrestrial and marine environments. The moon's presence establishes a reliable framework for life at night, structuring behavior, reproduction, and environmental interactions in ways that extend far beyond its simple reflection of sunlight. Ocean currents are the large scale movement of seawater across the globe, driven by differences in temperature, salinity, and wind patterns. These currents distribute heat, nutrients, and gases throughout the world's oceans, influencing climate systems and the health of marine ecosystems. The moon plays a key role in enhancing these currents through its effect on tides. Lunar gravity pulls on the oceans, creating tidal bulges that rise and fall across coastlines and continental shelves. The movement of these tides produces mixing of surface and deep waters, which interacts with the larger thermohaline circulation. This circulation, sometimes called the global conveyor belt, moves dense, cold water from polar regions to the equator and returns warmer, less dense water to higher latitudes. The tides driven by the moon help maintain the strength and regularity of this system by stirring water and aiding vertical and horizontal transport. Tidal mixing occurs when the rise and fall of water over the seafloor creates turbulence, blending layers of water with different temperatures and salinities. In shallow continental shelves, this effect is particularly strong as water encounters the seabed and slopes. The mixing redistributes nutrients, bringing them from the ocean floor into sunlit surface waters where photosynthetic plankton can use them. These plankton form the base of the marine food web, supporting fish, mammals, and birds. Without the moon, tidal mixing would be greatly reduced, and nutrient transport to surface waters would weaken. Over time, regions that rely on lunar-driven mixing for high productivity could experience reduced plankton growth, affecting the abundance and distribution of larger marine organisms. The interaction between tidal currents and the thermohaline circulation helps regulate global climate. Warm equatorial waters transported poleward release heat into the atmosphere, moderating regional temperatures. Cold, dense water sinking in polar regions drives deep ocean flows that carry oxygen and nutrients over long distances. Tides enhance this process by preventing water layers from becoming completely static. The vertical mixing helps maintain salinity gradients and temperature contrasts, which are essential for the continued movement of deep currents. Removal of the moon would diminish tidal forcing, slowing the movement of water and reducing the efficiency of heat transport. Over decades and centuries, this could produce measurable changes in climate patterns across continents, oceans, and atmospheric systems. Tidal currents also contribute to the exchange of gases between the ocean and atmosphere. Rising and falling water exposes more surface area to the air, promoting the absorption of carbon dioxide and the release of oxygen. These processes are critical for maintaining chemical balance in oceans and supporting marine life. Lunar tides increase the frequency and reach of this exchange, allowing gases to penetrate into deeper layers of water. Without the moon, weaker tides would slow gas mixing, reducing the speed at which carbon dioxide and oxygen are distributed. This would have subtle but cumulative effects on marine ecosystems and global climate feedbacks, as the oceans play a central role in regulating greenhouse gases. The moon's influence extends to coastal currents and estuaries. As tides rise and fall, they drive horizontal movement along the shore, redistributing nutrients, the sediments, and organic material. This flow feeds wetlands, mangroves, and tidal flats, which act as nurseries for fish and filter pollutants from the water. Tidal currents interact with river inflows to create complex circulation patterns in these areas. Without the moon, these processes would be weaker, reducing nutrient availability and potentially altering the structure of coastal ecosystems. Sediment transport would slow, affecting shoreline shape and the development of protective features such as barrier islands. Over centuries, the accumulation of these effects could change the physical and biological landscape of coastal regions. Deep ocean currents also respond to tidal forces. Lunar tides produce subtle, vertical movements that break down stratification, mixing dense, nutrient rich water from the ocean floor with lighter surface layers. This vertical circulation supports the growth of phytoplankton by supplying essential minerals like nitrogen and phosphorus to the sunlit zone. Phytoplankton, in turn, fix carbon through photosynthesis, forming the foundation of carbon sequestration in the ocean. A reduction in lunar-driven mixing would decrease nutrient supply to surface waters, limiting primary production. Over time, this could reduce the efficiency of the ocean as a carbon sink, altering global carbon cycles and influencing long-term climate regulation. Oceanic mixing also affects temperature distribution. In equatorial regions, warm surface waters are transported toward the poles, where they release heat into the atmosphere. Cold polar water sinks and moves toward the equator, creating a cycle of heat redistribution. Lunar tides enhance this movement by agitating water layers, preventing stagnant zones from forming. Without the moon, vertical mixing would be less effective, and heat would remain trapped in certain regions for longer periods. This could exaggerate temperature extremes, warming some areas while cooling others. The resulting shifts in heat distribution would impact atmospheric pressure, wind patterns, and precipitation, producing ripple effects on regional and global climates. The moon's gravitational influence also interacts with seasonal changes in ocean currents. During certain times of the year, tides coincide with monsoons, equinoxes, or solstices, amplifying movement in coastal and shelf regions. These periods of increased circulation help distribute nutrients and influence the timing of biological events such as plankton blooms. The predictable pattern of lunar tides ensures that these interactions occur consistently, providing stability for marine food webs. Without lunar influence, seasonal synchronization of these processes would weaken, potentially affecting the timing and success of reproductive and feeding cycles for many marine species. Tides affect deep ocean mixing in polar regions as well. In areas covered by sea ice or ice shelves, tidal currents push water beneath the ice, allowing dense cold water to sink and contribute to thermohaline circulation. This movement helps maintain oxygen levels and nutrient transport in deep water, supporting organisms that live far from the surface. If the moon disappeared, tidal energy in polar regions would be greatly reduced, slowing the formation of dense water and weakening a critical driver of global circulation. The consequences would extend far from the poles, as slower deep water movement would reduce the efficiency of heat, nutrient, and oxygen transport across oceans. Lunar driven ocean currents also affect climate indirectly through feedback loops. For example, stronger tides encourage upwelling, which brings cooler, nutrient rich water to the surface. This upwelling supports large fish populations and influences atmospheric CO2 levels by regulating phytoplankton growth. Reduced tidal mixing would diminish upwelling, potentially increasing surface temperatures in certain regions and altering the capacity of oceans to absorb carbon. These changes could affect atmospheric CO2 concentrations, producing long term effects on global temperature and climate patterns. Tidal currents shape the distribution of salt and freshwater in ocean basins. By stirring water and creating horizontal and vertical flows, tides help maintain consistent salinity gradients. Salinity, in combination with temperature, determines water density and drives the sinking of dense water masses. If lunar tides were absent, the uniformity of salinity distribution would decrease, altering the density driven flows essential to the thermohaline circulation. These shifts would produce changes in regional climates as the movement of heat through the oceans slows and the exchange of gases between water and atmosphere diminishes. Coastal and open ocean currents interact to produce nutrient hotspots. Areas where tidal flows meet large scale currents often have higher biological productivity due to the combination of mixing, nutrient supply, and sunlight. Fish and marine mammals concentrate in these regions, relying on the predictable movement of water to access food. Without lunar influence, the consistency of these hotspots would decline. Populations of predators and prey would adjust slowly, with some regions experiencing reduced abundance and altered community structures. Over decades and centuries, the absence of tidal reinforcement would reshape ecosystems across multiple ocean basins. The moon's effect on ocean currents links directly to global climate feedbacks. By driving tides that mix water vertically and horizontally, the moon helps distribute heat, nutrients, and gases efficiently. Removal of this influence would produce slower circulation, weaker upwelling, and reduced gas exchange. Climate systems dependent on oceanic transport of energy would adjust gradually, changing rainfall patterns, temperature distribution, and storm intensity. The interaction of tides and thermohaline circulation is therefore a critical component of Earth's environmental stability, demonstrating how the moon's gravitational pull extends far beyond the visible motion of water along shorelines. The moon exerts gravitational forces not only on Earth's oceans, but also on the solid crust of the planet. These tidal forces create slight but measurable stresses within the lithosphere. As the moon pulls on Earth, it generates small flexing of the crust, producing strains that shift rock layers by millimeters over the course of a day. These movements are most noticeable in regions where the crust is thinner or more fractured. While the stresses are minor compared to the forces involved in plate tectonics, they are continuous and predictable. The cyclical nature of lunar tides produces a rhythm of stress that interacts with tectonic forces, adding a subtle modulation to seismic and volcanic activity. Seismic studies have shown that earthquakes can correlate with the timing of tidal maxima and minima. While tides alone do not cause earthquakes, they can trigger events in regions where stress is already near a critical threshold. For example, shallow earthquakes along mid-ocean ridges, subduction zones, and transform faults sometimes occur more frequently during periods of high tidal stress. This correlation demonstrates that the moon's gravitational pull, though small, has a measurable effect on the timing of seismic activity. By subtly altering the stresses in the crust, lunar tides contribute to the release of built up energy in faults that are otherwise near failure. Volcanic activity can also be influenced by lunar tidal forces. The movement of magma beneath the crust responds to variations in pressure and stress. As tidal forces flex the crust, magma chambers may experience slight changes in pressure, which can affect the timing of eruptions. Observations in some volcanic regions show minor increases in eruption frequency or seismic tremors during periods of peak tidal stress. This effect is not sufficient to cause eruptions independently, but it can modulate ongoing geophysical processes. The presence of the moon ensures that these forces act with regularity, creating a predictable cycle that interacts with the natural rhythms of Earth's interior. Without the moon, these tidal stresses would vanish, removing a source of periodic modulation in crustal forces. Earthquakes would still occur due to tectonic motion, but the timing would no longer align with lunar cycles. Seismic energy might accumulate slightly differently, and the predictable pattern of stress relief would be altered. Over long periods, the absence of this modulation could influence the distribution of earthquakes, particularly in regions that currently respond to tidal forcing. While the magnitude of large tectonic events would remain primarily controlled by plate movement, minor quakes and tremors could become less synchronized with natural cycles, subtly altering seismic patterns worldwide. The moon's gravitational influence extends to the movement of Earth's mantle. As the crust flexes under tidal stress, the mantle experiences minor deformations that affect convection currents. These currents drive the motion of tectonic plates, transporting heat and material from the planet's interior to the surface. While the primary drivers of mantle convection are thermal gradients and density differences, tidal forcing contributes small oscillations that influence the flow of molten rock. The absence of the moon would eliminate this oscillation, slightly altering the mechanical environment of the mantle and the transfer of energy through the lithosphere. Over geological timescales, these small changes could affect the pattern and rate of plate movement. Coastal regions are particularly sensitive to tidal stresses because the land meets the ocean. The rise and fall of water combined with lunar gravitational pull flexes coastal faults and continental shelves. This flexing can trigger minor earthquakes and influence sediment movement, shaping coastlines slowly over time. Without the moon, the tidal amplitude in these areas would decrease, reducing the frequency of minor seismic events and altering the deposition and erosion of sediments. Shoreline development, sediment transport, and the formation of estuaries could follow slightly different patterns, demonstrating the moon's indirect influence on the geophysical evolution of coastal zones. Deep faults within continents also respond to lunar tidal forces. Even in regions far from oceans, gravitational pull from the moon produces tiny vertical and horizontal strains. These forces can modulate the timing of small-scale seismic events, influencing the sequence of tremors along long fault lines. Observations indicate that regions with a high density of fractures, such as the Basin and Range in North America or rift zones in Africa, show measurable periodicity in minor seismic activity that aligns with the lunar cycle. Removal of the moon would erase this periodic influence, leaving only tectonic stress accumulation to determine earthquake timing. The overall mechanics of plate motion would remain, but the regularity imposed by lunar tides would disappear. Volcanoes are sensitive to the flexing of the crust caused by tidal forces. The overlying rock layers shift under lunar pull, creating changes in pressure within magma chambers. In some cases, this can influence the release of gases and the ascent of molten rock toward the surface. Tidal modulation can trigger small earthquakes or harmonic tremors that precede eruptions. The absence of lunar tides would reduce this modulation, potentially affecting the subtle precursors that occur before volcanic activity. The overall volume and intensity of eruptions would not change significantly, but the temporal patterns of minor events leading up to eruptions could become less consistent. Earth tides affect the distribution of stress along fault lines, influencing the formation and movement of fractures. As stress builds in the lithosphere, the timing of small slips or micro earthquakes can coincide with peaks and troughs of tidal forcing. These micro events contribute to energy release that may delay or accelerate larger quakes. Without the moon, this modulation would be lost, and faults might accumulate energy differently, slightly altering the dynamics of earthquake sequences. Over millions of years, these subtle shifts could influence the evolution of fault networks and the regional distribution of seismic hazard. The interaction between tidal forces and volcanic plumbing systems is subtle but measurable. Magma is viscous and responds slowly to pressure changes. Lunar tides produce periodic variations that, although small, can influence magma movement within chambers, conduits, and dikes. These effects are most noticeable in volcanoes already in a critical state, where minor stress changes can tip the system towards small eruptions or gas release. In the absence of the moon, these small cyclical pressures would vanish, removing a natural pacing mechanism in the crustal and magmatic system. The long term rhythm of volcanic tremors and minor eruptions would adjust to rely solely on thermal and tectonic forces. Tidal stresses also affect fault friction. The slight flexing of rock under lunar gravity changes the normal and shear stress on fault surfaces, occasionally promoting or delaying slip. Scientists measure these effects using sensitive seismometers, detecting correlations between tidal phase and microseismic events. The removal of the moon would eliminate these small variations, creating a more uniform stress environment. While tectonic motion would continue to generate earthquakes, the predictability and periodicity linked to lunar cycles would disappear. The Earth's crust would remain dynamic, but the subtle guidance provided by tidal forces would be gone. Long term geological processes are shaped by repeated tidal stressing. Over millions of years, the moon's pull has contributed to the slow flexing of plates, the cycling of minor faults, and the maintenance of fractures that influence magma pathways. Erosion and sedimentation along these faults are also influenced by tidal modulation. Without the moon, these slow, cumulative processes would continue, but without the regular oscillations that add fine scale variability. Geological formations might develop slightly differently, reflecting the absence of lunar driven flexing, while the scale of major tectonic and volcanic events would not change drastically. The timing and sequence of smaller events would adjust. Earthquakes, volcanism, and tidal forces are connected to other systems on the planet. For instance, volcanic outgassing influenced by tides contributes to atmospheric composition, while seismic activity shapes topography and drainage patterns. The moon's presence integrates into these processes by providing a steady source of minor modulation in stress and pressure. Removal of the moon would simplify the rhythmic interaction of these forces, potentially changing how energy is distributed through Earth's crust and mantle over long timescales. The subtle timing of tremors and eruptions would become more irregular, affecting the interplay of geological and surface processes. The moon's role in geophysical processes illustrates its influence beyond oceans and rotation. By producing tidal stresses in the crust and mantle, it affects earthquakes, volcanic activity, and the transport of energy through the lithosphere. The regularity of these stresses interacts with tectonic forces, guiding the timing of small seismic events and the movement of magma. Without the moon, this subtle modulation would disappear, leaving tectonics to operate under purely internal forces. Earth's crust would continue to move, volcanoes would still erupt, and earthquakes would occur, but the predictable lunar rhythm embedded in these processes would vanish, demonstrating the moon's quiet yet persistent role in shaping the geophysical character of the planet. Many species on Earth rely on the moon to regulate biological rhythms. Lunar phases influence reproductive cycles, feeding schedules, and migration patterns. Sea turtles, for instance, hatch during the night near a new moon when darkness is greatest. This timing reduces the risk of predation, allowing hatchlings to reach the ocean more safely. Other marine animals, such as certain species of fish and invertebrates, spawn according to specific lunar phases. The predictable sequence of waxing and waning light provides a reliable signal for the coordination of reproductive behavior. If the moon disappeared, these timing cues would vanish, potentially altering reproductive success and population dynamics for many species. Migration patterns in animals are also connected to lunar cycles. Some birds use the moon to navigate during long nocturnal flights, using its position as a reference point alongside the stars. Insects, such as moths and other flying arthropods, orient themselves by moonlight during nightly movements. Without the moon, orientation cues would be reduced, forcing these species to rely entirely on stars or magnetic fields. Migration schedules could shift as species adapt to the absence of lunar guidance, possibly leading to increased energy expenditure and changes in survival rates. The disappearance of the moon would slowly alter patterns of movement across continents and oceans. Marine species show a strong dependence on the moon for synchronized spawning events. Coral reefs, for example, release eggs and sperm during specific nights that follow a full moon, ensuring simultaneous fertilization and maximizing reproductive success. Other invertebrates and fish also coordinate spawning with tidal rhythms tied to the moon. Removal of the moon would break these timing cues, causing reproductive events to become less synchronized. Reduced synchronization would decrease fertilization rates and could affect the abundance and distribution of species that rely on mass spawning for population maintenance. Nocturnal animals rely on lunar illumination to regulate activity. Predators such as owls, big cats, and some fish hunt more effectively under full moonlight, while prey species adjust behavior to reduce risk of detection. Moonlight also affects amphibians, insects, and small mammals that are active at night, influencing feeding and movement. Without the moon, nights would be consistently darker, and animals would gradually adapt to uniform low light conditions. Hunting strategies, foraging behavior, and sheltering habits would change, with ripple effects across ecosystems. Predator prey dynamics, energy flow, and competition for resources would adjust to the absence of lunar influence. Plant biology is influenced by lunar cycles in subtle ways. Some seeds are sensitive to the duration and intensity of moonlight for germination. Flowering in certain plant species is timed to lunar phases, especially in coastal or tidal regions where the moon affects water levels. Without the moon, the regular pattern of nighttime illumination would be lost. While sunlight continues to drive photosynthesis, these nocturnal or phase sensitive processes would need to rely on other environmental cues, such as temperature or day length, which may not be as precise. Over time, the absence of lunar guidance could alter growth cycles and reproductive timing in plants. Tidal rhythms influence feeding and reproduction in coastal and estuarine species. Crabs, mollusks, and fish often synchronize activity with high and low tides, which correspond with lunar positions. Shorebirds and other animals feeding in these areas adjust behavior to tidal exposure, timing foraging to maximize food availability. Without the moon, tidal amplitudes would decrease, and the predictable schedule of feeding and reproduction would change. These shifts could influence energy transfer through food webs, potentially altering population structure and the distribution of species along coastlines. Lunar influence also affects nocturnal migration in the ocean. Many planktonic species rise to the surface at night and descend during the day in vertical migrations linked to light cycles, including moonlight. This behavior is critical for feeding, predator avoidance, and nutrient cycling. The disappearance of the moon would remove a guiding cue, leading to changes in vertical migration timing and patterns. Over time, altered plankton movement could influence the availability of food for fish, marine mammals, and seabirds, creating cascading effects in marine ecosystems. Reproductive behaviors in terrestrial species are influenced by lunar cycles as well. Some amphibians, such as frogs and toads, time mating calls to specific moon phases. Insects, including beetles and moths, emerge and mate in response to moonlight cues. Mammals that rely on nocturnal activity for breeding also show variations linked to lunar brightness. Removal of the moon would eliminate these regular patterns, forcing species to adjust to alternative cues. Changes in timing could reduce reproductive success and gradually shift population dynamics. Predator prey relationships are structured in part by lunar cycles. Increased light during full moons allows predators to hunt more efficiently, while prey species may reduce activity or seek cover. During new moons, darkness favors prey survival and alters hunting strategies. The predictable monthly variation in predation pressure contributes to ecological balance. Without the moon, darkness would be constant at night, eliminating this cyclical pressure. Predators and prey would adjust behavior over generations, gradually changing patterns of population density, movement, and competition. The moon's absence would also affect pollinators that operate at night. Certain moths and beetles are active under moonlight, visiting flowers and transferring pollen. These interactions are timed to lunar cycles and contribute to plant reproductive success. Darker nights without lunar illumination would alter pollination schedules and potentially reduce plant reproduction in species dependent on nocturnal pollinators. The resulting ecological adjustments would influence the structure of plant communities and the animals that rely on them for food and habitat. In coastal ecosystems, tides influenced by the moon shape these distribution and behavior of species. Intertidal zones experience cycles of submersion and exposure that are critical for feeding, breeding, and sheltering. Moon-driven tides provide a predictable rhythm for these processes. Without the moon, tidal ranges would decrease, altering exposure times and habitat availability. Species that rely on regular tidal cycles for feeding or reproduction would gradually adapt or relocate, leading to changes in species composition and ecological interactions across tidal zones. The removal of lunar influence would affect energy flow within ecosystems. Many species time feeding, reproduction, and movement according to lunar cues, creating synchrony in activity that stabilizes food webs. Without these cues, temporal distribution of activity would become less structured. Predator-prey interactions, nutrient cycling, and competition for resources could shift, producing gradual reorganization of ecological networks. The moon's presence provides the natural pacing mechanism that synchronizes behavior and energy transfer across species. Even in terrestrial forests, moonlight influences activity. Small mammals, reptiles, and insects adjust movement and feeding patterns according to lunar illumination. Predation pressure and competition interact with these patterns, creating temporal niches that reduce overlap between species. Without the moon, these nocturnal schedules would flatten into uniform darkness, altering interactions among species. Behavioral adjustments would occur slowly, modifying feeding efficiency, reproductive timing, and spatial distribution within forest ecosystems. Marine migration is affected by the combined influence of moonlight and tides. Many pelagic species move towards spawning grounds or feeding areas in alignment with lunar cycles. The moon's disappearance would disrupt these timing cues, introducing variability in the location and success of migration events. Over time, species would adapt to new schedules based on alternative environmental signals, but the reliability and synchronization provided by the moon would be lost, with potential consequences for population connectivity and reproductive success. The moon's influence extends across multiple ecological scales, from plankton to large mammals, from intertidal zones to deep forests. Lunar cycles regulate activity, reproduction, and movement. Removal of the moon would eliminate these signals, leading to uniform nocturnal darkness, reduced tidal rhythm, and altered ecological timing. Species would gradually adjust, but the predictable pacing that organizes biological and ecological processes would be lost. The moon's presence is integral to the structure and functioning of Earth's ecosystems, providing a monthly rhythm that supports the balance and coordination of life across the planet. Throughout history, humans have relied on the moon to organize time and plan activities. Lunar calendars, based on the cycle of phases from new moon to full moon, have been used by many cultures for thousands of years. Agricultural practices, religious events, and social schedules often depended on the predictable rhythm of lunar cycles. Planting and harvesting schedules were adjusted according to the moon, as certain phases were believed to favor growth or germination. Navigation, especially before the invention of modern instruments, was aided by the moon's position in the sky, providing a reliable reference for orientation at night. The disappearance of the moon would remove a long standing environmental guide, requiring humans to rely entirely on solar cues or artificial systems for timekeeping and orientation. In astronomy, the moon's absence would alter the background conditions for observations. Moonlight currently affects the brightness of the night sky, influencing the visibility of stars and faint objects. Observatories plan observations around the lunar cycle to reduce interference from bright nights. Without the moon, nights would be darker, allowing longer periods for observing faint celestial objects without moonlight interference. However, the disappearance of the moon would also eliminate a natural reference for calibrating instruments, tracking motion, and testing observational models. Lunar based measurements, including studies of tidal interaction and Earth Moon distance, would no longer be possible, slightly reducing the scope of certain observational programs. Satellite operations are influenced by lunar position and gravitational effects. The moon contributes small but measurable perturbations to satellite orbits, which are accounted for in calculations for navigation, communication, and observation satellites. These effects help refine predictions of orbital paths and maintain stability in high precision systems. Without the moon, orbital dynamics would simplify in some ways, but previously modeled trajectories would require adjustment. Systems that depend on long term predictions of gravitational influences, including some space debris tracking and Earth observation satellites, would need recalibration to account for the absence of lunar pull. Tidal energy systems, which generate electricity by harnessing the movement of water in tides, rely directly on the moon. Coastal turbines and other tidal generators depend on the rise and fall of water driven primarily by lunar gravity. Removing the moon would drastically reduce tidal ranges, making tidal power generation far less effective. Regions that currently use tidal energy as part of renewable infrastructure would experience a decline in output. Engineers and planners would need to develop alternative energy sources or rely more heavily on other forms of renewable energy. Over time, communities dependent on predictable tides would face challenges in maintaining stable electricity supply from tidal systems. Coastal planning and infrastructure have historically been designed around tidal behavior influenced by the moon. Ports, harbors, and navigational routes rely on predictable high and low tides for safe operation. Bridges, seawalls, and flood defenses account for tidal ranges when determining clearance and structural requirements. If the moon disappeared, tidal amplitude would decrease and the timing of tidal cycles would change, requiring adjustments to infrastructure management. Long term planning for flood control, shipping schedules, and waterway maintenance would need to adapt to altered ocean behavior, potentially affecting commerce, transport, and urban development in coastal regions. The moon also serves as a stabilizing factor in geophysical cycles that indirectly affect human activities. Coastal erosion, sediment transport, and shoreline development are influenced by tidal forces. Removal of lunar tides would alter these processes, impacting coastal settlements over decades and centuries. Communities located in estuaries and river deltas would experience changes in water flow, sediment deposition, and shoreline shape. Infrastructure planning would need to account for these shifts, adjusting construction, flood defenses, and resource management strategies to match new conditions. Human observation of natural rhythms has been guided by the moon. Cultural practices, such as timing of festivals or hunting and fishing cycles, have historically synchronized with lunar phases. Loss of the moon would remove a familiar monthly marker requiring replacement with artificial systems or purely solar based calendars. While modern technology reduces dependence on natural markers, many historical and cultural records are based on lunar timing. Understanding and aligning with these systems would require reinterpretation and adjustment in both historical studies and ongoing cultural practice. Long term navigation, particularly at sea, has been affected by the moon. Sailors have used lunar altitude and phase to assist in determining latitude and time. Before GPS and modern instruments, the moon provided an important reference for nocturnal navigation. Without the moon, traditional methods would no longer function, and even modern automated systems would need recalibration for calculations previously using lunar data. Lunar influence also affects the timing of tidal currents, which has been crucial for navigation, fishing, and port operations. The absence of the moon would alter these currents, affecting both safety and efficiency in marine transport. Satellite communication and orbital observation are sensitive to gravitational variations influenced by the moon. Even minor changes in Earth's shape caused by lunar tides affect atmospheric density at high altitudes, which in turn impacts drag on low orbit satellites. Without lunar tides, orbital decay rates would change slightly, requiring recalculation of fuel requirements, satellite positioning, and deorbit planning. Long term satellite networks and constellation management would need to adapt to these subtle shifts, ensuring continued precision in global communications, navigation, and observation. Military and scientific operations that rely on tides would also be affected. Coastal and naval planning often uses predictions based on lunar cycles. Submarine navigation, landing operations, and training exercises depend on the timing and magnitude of tides. The moon's disappearance would eliminate a major source of predictability in these systems, requiring reliance on wind driven tides or smaller solar influences. Planning models for safety, logistics, and operational timing would need to adjust to the altered environment. Artificial lighting in urban areas partially masks the moon's influence, but natural rhythms still persist in less developed regions. Lunar illumination has historically guided nighttime activity, from travel to agricultural work. The disappearance of the moon would create consistently darker nights, particularly in areas without artificial lighting, altering human activity patterns. This effect could influence planning in rural or coastal communities, as well as cultural practices that follow lunar cycles, including festivals and agricultural labor. Long term climate monitoring and environmental planning also intersect with lunar influence. Coastal erosion rates, tidal sediment transport, and tidal mixing in estuaries are considered in predicting sea level rise, flood risk, and ecosystem resilience. Without the moon, predictive models for these processes would need revision. Infrastructures such as levees, ports, and drainage systems would be designed under new conditions, accounting for reduced tidal energy and altered coastal dynamics. Urban and regional planners would need to incorporate these changes into long term development strategies. The moon's absence would affect a wide range of human systems simultaneously on timekeeping, navigation, energy production, infrastructure, planning, and observation all integrate lunar influence. Removal of this single natural element would produce cascading adjustments across multiple domains. Engineers, scientists, and policymakers would need to develop new frameworks for predicting environmental behavior and managing human activity. The moon's presence provides stability, predictability, and reference in multiple technical and societal systems, illustrating its indirect but pervasive role in human civilization. The moon affects Earth in many ways, from ocean tides to the behavior of living species, from rotation and climate to human activities. Its gravitational pull shapes the rise and fall of the seas, influencing the flow of currents and the mixing of nutrients. Tidal forces interact with the thermohaline circulation, helping distribute heat and minerals across oceans. Without the moon, tides would be smaller, ocean mixing would weaken, and nutrient transport would decline. This change would ripple through marine ecosystems, affecting plankton growth, fish populations, and predator prey relationships. Energy transfer in food webs would adjust to new patterns, and species dependent on lunar cycles for reproduction or migration would adapt to alternative cues over time. The stability of Earth's rotation is closely tied to the moon. By absorbing angular momentum and producing tidal friction, the moon slows the planet's spin gradually. Its removal would cause Earth to rotate slightly faster over long periods. Shorter days would change the timing of environmental cycles, affecting temperature variation and weather patterns. The moon also stabilizes the axial tilt, preventing large fluctuations in orientation that influence seasons. Without the moon, the tilt could vary more over millennia, leading to unpredictable seasonal intensity and long term climate shifts. This effect would interact with ocean circulation, atmospheric pressure, and global temperature distribution, producing complex environmental consequences. Lunar illumination organizes nocturnal behavior. The cycle of phases provides a rhythm for activity at night in plants, animals, and humans. Predators, prey, pollinators, and migrating species all adjust their schedules to the moon's brightness. The disappearance of lunar light would create uniform darkness at night, removing these temporal cues. Biological rhythms that depend on moonlight or lunar timing would shift, with animals and plants slowly adapting to alternative environmental signals. Marine species that spawn in synchrony with lunar phases would experience reduced coordination, altering reproductive success and population structure. Terrestrial nocturnal species would adjust foraging and movement patterns, affecting competition, predation, and resource use. Geophysical processes are subtly modulated by the moon. Tidal forces induce stress in the crust and mantle, influencing earthquakes, minor tremors, and the movement of magma. Small variations in pressure caused by lunar tides can modulate volcanic activity and fault slip timing. Without the moon, tectonic forces would continue to operate, but the regular lunar rhythm of stress and strain would vanish. Earthquakes and eruptions would occur according to internal dynamics alone, and the timing of minor events would lose periodicity. Coastal regions that experienced tidal flexing would have altered sediment transport and shoreline development, with long term effects on landscape formation and erosion patterns. Human activities are also linked to lunar cycles. Calendars, agriculture, navigation, fishing, and cultural events have historically relied on the moon. Lunar illumination affects nighttime planning, while tidal knowledge supports ports, energy systems, and infrastructure design. Removing the moon would alter tidal patterns, requiring adaptation in tidal energy generation, coastal engineering, and marine operations. Navigation and satellite tracking would need adjustments due to changed orbital dynamics and tidal influence. Cultural practices tied to lunar phases would no longer align with environmental cues, requiring reinterpretation and new planning strategies. Across civilizations, the moon has provided a consistent reference for rhythm, timing, and environmental awareness. The absence of the moon would gradually reshape ecological systems. Nutrient cycling in oceans would change due to weaker mixing, affecting phytoplankton growth and marine food webs. Migration, reproduction, and feeding schedules would adjust in response to the absence of lunar cues. Predation and competition patterns would shift, and plant and animal species would adapt to uniform night conditions. Coastal and estuarine systems would experience altered exposure, water flow, and habitat structure. The cumulative effect would be a slow transformation of ecosystems at multiple scales, affecting biodiversity, species distribution, and population dynamics. Over centuries and millennia, life would reorganize under new environmental rhythms. Climate patterns would respond to altered ocean circulation and rotation. Reduced tidal mixing would weaken heat transport, while changes in axial tilt could produce more extreme seasonal variability. Surface and deep ocean temperatures might diverge from previous patterns, affecting weather systems, rainfall, and storm formation. Polar regions, which contribute dense water to thermohaline circulation, would experience less tidal influence, reducing global water movement. These physical changes would interact with ecological shifts, creating feedback loops that adjust energy flow, species behavior, and human activity simultaneously. The environment would slowly reach a new equilibrium without the moon, with both predictable and unexpected consequences. Human infrastructure and planning would need to respond to these changes. Ports, levees, bridges, and tidal energy systems would operate under altered conditions, requiring long term adjustments. Coastal cities might see shifts in erosion, sediment deposition, and tidal patterns. Navigation would need new reference points, and energy systems dependent on tides would lose efficiency. Agricultural planning and cultural timing would no longer follow lunar cycles, requiring alternative methods to coordinate activities. In combination with ecological and climatic adjustments, the moon's removal would ripple through human systems, demonstrating the interconnectedness of natural and human designed environments. The moon's influence extends to multiple scales simultaneously, from microscopic plankton to large mammals, from daily ocean tides to millennia long climate patterns. Lunar effects provide a stabilizing rhythm. Biological, physical, and human systems are all linked to lunar forces, forming an integrated network of environmental and societal interactions. Removing the moon would not halt these processes, but it would remove a unifying driver that organizes cycles and provides predictability. Life and human activity would adapt, but the subtle structure imposed by lunar presence would be lost, resulting in gradual changes to behavior, distribution, and rhythm across the planet. In summary, the moon shapes Earth through gravitational, geophysical, ecological, and cultural pathways. Its tidal pull drives ocean currents, influences climate, and modulates crustal stress. Its light and cycle coordinate biological behavior. Its predictable presence supports human planning, observation, and energy systems. Without the moon, Earth would experience reduced tidal amplitude, faster rotation, altered axial tilt, and changes in nocturnal light cycles. Marine, terrestrial, and human systems would adapt to new conditions, reorganizing rhythms and schedules. The interconnectedness of ocean, atmosphere, lithosphere, biosphere, and human systems highlights the importance of the moon as an organizing factor in Earth's environment. While many processes would continue without the moon, the absence of its influence would gradually alter equilibrium across oceans, ecosystems, climate, and human activities. Species, populations, and systems would adjust, but the predictability and synchronization provided by lunar cycles would vanish. Tides would shrink, nocturnal light cycles would flatten, reproductive timing would shift, and coastal dynamics would change. Ocean circulation and climate feedbacks would adjust to the missing gravitational influence. Earth would remain habitable, but with new environmental rhythms, reorganized ecosystems, and modified human operations. The long term effect of the moon's disappearance demonstrates the complex interdependence of planetary systems. Physical, biological, and human processes operate in continuous cycles, many of which rely on lunar forces. Loss of this central influence would propagate changes slowly but consistently, highlighting the moon's integral role in shaping life, climate, and human infrastructure. Observing the interconnected consequences emphasizes the value of the moon as more than a celestial object. It functions as a stabilizing factor for Earth's rotation, tides, climate, ecology, and human systems. Its absence would be felt across multiple temporal and spatial scales, altering the pattern of life and environment over centuries and millennia. In conclusion, the moon provides a consistent force that interacts with Earth's oceans, atmosphere, lithosphere, and biosphere. Its gravitational pull creates tides, influences currents, and stabilizes rotation. Its light regulates nocturnal activity, reproduction, and migration. Its presence supports human understanding, planning, and technological systems. Removing the moon would set in motion gradual changes affecting tidal energy, coastal infrastructure, ecological balance, climate patterns, and human routines. Earth's systems would reorganize under new conditions, eventually reaching a new equilibrium. The moon's influence is pervasive and enduring, linking physical, biological, and human processes in a rhythm that has persisted for millions of years. The combined impacts of lunar removal would be subtle in the short term but cumulative over long timescales. Oceans, ecosystems, climate, and human society would slowly adapt. Energy flows would reorganize. Species would adjust reproductive and migratory timing, and infrastructure would require modification. Earth would maintain habitability, but the natural cycles shaped by the moon would be replaced by new rhythms dictated by internal and solar influences. The stability, predictability, and coordination provided by lunar presence would be lost, demonstrating the moon's central role in maintaining the balance of Earth's environmental and human systems.